All right, well, what we're going to do is we're going to go through the part C of 2012, number 1. And what we have for 0 to 20, the average temperature of water in the tub is this right here, 1/20th of the integral from 0 to 20 of Wt dt. We're going to use a left Riemann sum, with 4 subintervals indicated by the data, the table to approximate. We're going to approximate this value right here. Does this approximate overestimate, underestimate the average temperature over the 20 minutes? Explain your reasoning. Okay. Well, right here, what we know is it says that this is a strictly increasing function. All right, and so with that, we can see that all the values are going higher and higher and higher. We're going from 0 to 20, and what this is asking us to do is this is asking us to find the average temperature. So we're finding the average temperature, which makes it lots of sense. And so, because if you recall, I did a previous video on this, and then when we have a value and we're integrating a value, we're taking all those values, and then when we divide by this gives us an average. Okay, so we're not integrating a rate to go back to the antiderivative to the beginning. We are actually integrating the function, and so to integrate the function, to go back to the function, really all we're doing is just adding up all the values of the function from 0 to 20, which generally will tell us we're trying to find an average temperature, or in this case, average temperature, but an average value. So, in any case, because this is simply increasing, if we kind of like plot this out and we think about this, all right, is this going to be an over and underestimate? I'm going to answer that question first. And if we plot this values and we go from 0 to 20, and you just kind of think about this, and what we're going to do is, because this is increasing, okay, we know we're doing a left Riemann sum, and so we are actually taking all the values that are less than the actual values. So we know that all the values will be under the curve. So because this is increasing, we would say that this is a underestimate. All right. So the value we're getting is an underestimate. So I'm just going to put that down. All right. Does this approximation? The approximation is a underestimate because W of t is increasing. And that's what we know with that. Okay. So now let's do the Riemann sum. Now, if you recall, Riemann sums, we're counting rectangles. All right. We're finding areas of rectangles. And the key is when we're finding areas of rectangles, you have to remember that we're taking length times width, or base times height. All right. And in this case, our base is always going to be delta, well, in this case, delta t. Okay. And this says that we're using a Left Riemann with 4 subintervals indicated in the table. Now, notice how they say 4 subintervals, but they do not say that those subintervals are going to be equal. Okay, they're not going to be equal. So we need to find our delta t, the difference in our subintervals, and then we need to find our heights. So right here, if you look up here, we have 1, 2, 3, and 4 rectangles. So it's going to be rectangle 1, rectangle 2, rectangle 3, and rectangle 4. Okay, so now the question is, what's the area of each one of these rectangles? So if I go up here, because that's my room, rectangle 1 area, well, we're going to take delta x, our width. Well, our width, you see, is going from 0 to 4. So actually, that delta t is actually going to be 4 minus 0, which is 4, times the Riemann sum with left Riemann sum. So on this first one, which do we use for our height? The height is going to be the left side, which is going to be that value, which is going to be 55. We're going to add that to our second rectangle, and our second rectangle is going to be, all right, delta t, which is going to be 9 minus 4. So this delta t is actually going to be 5. And then our left side of this rectangle is going to be 57.1. We're then going to add that to our third rectangle. And our third rectangle, you can see right here, going from 15 to 9, that's going to be 6. And then we're going to use 61.8. So 6 is our delta T, and we have 61.8. And then finally, for our fourth rectangle, we are going to be using our height, which is 67.9, and we see that our delta T, the difference between these, all right, is going to be 5. So if I just put here, delta T is 4, delta T for this one is 5, delta T for this one is 6, and delta T for this rectangle is 5 again. And you see how they're all a little bit different. Okay, that's 5. All right, and so that is going to be key when we're doing this. And I'm just going to go right there, which is 67.9. Okay, so we have our rectangles, and so now we want to find out our areas. All right, so so we have this right here. This is going to be our W of T of N, whatever values we plug in there for that one. So what is our values going to be? Well, we're going to have 4 times 55 plus 5 times 57.1 plus 6 times 61.8, and that's going to be plus 5 times 67.9. And that's going to be approximately the integral from 0 to 20 of WT dt. Okay, and I'm going to put an approximation symbol because we're going to approximate that value. So now we go to your calculator and we want to figure that out. All right, so 4 times 55 plus 5 times 57.1 plus, and I'm putting my calculator, so maybe you're doing the same. And you probably maybe fast forwarding through some of this stuff depending on if you got it. All right, so I got right here, so this value is 1,215.8, and that is going to be, all right, the value of that one. So the average temperature of water. Now this is actually the temperature, all right, increased between 0 and 20 by 1,215.8 degrees Fahrenheit, going from there. But now we have to divide that by 20, all right, divide by 20. And so to find our average, well, we're going to multiply that by 1215.8, and that's going to give us, all right, so our average temperature, 60.79, okay, degrees Fahrenheit. That was our average temperature right there. So does this approximate, overestimate, or underestimate? And we say the approximation, if we want to put it in context of approximation of, oops, hello, oopsies. All right, approximation of 60.79 degrees Fahrenheit is a underestimate because WT is increasing on the interval. All right, from 0 to 20 minutes. Okay, and there we go, and that's our answer. Okay, so once again, using Riemann sums, don't forget to multiply by 1/20th at the end. This right here, all right, the Riemann sum gives you the integral. The 1/20th gives you the average. Okay, I see a lot of students when they do problems like this, when I do them in class and whatnot, they always take it and divide by 20. No, that's not how you find a integral. An integral is this part. That's what we're using the Riemann sum for, and we're taking the 1/20th. That's how we get the average. Okay, hopefully that makes sense. All right, final problem, final question. All right, right here, it says in here, this first one, it says that D for 20 to 25, the function W that models the water temperature has a first derivative given by this. Okay, so here's our first derivative. Based on the model, what is the temperature of the water at time t equals 25? Okay, so we are given a rate. Okay, so that's the first derivative. So that's the rate of the temperature. Okay, all right, that's the rate. And we want to figure out what is the temperature. Well, in order to go from a rate to an amount, we are working backwards. And the only thing is, based on this, we are looking for what W is. But notice that W the degrees in Fahrenheit only goes from 0 to 20, and that's why they give us this other equation. But this equation is from 20 to 25. So in order to figure out this, we're going to use the fundamental theorem of calculus. All right, FTC. That's the fundamental theorem of calc. Okay, that's what that stands for. And what the fundamental theorem of calculus says is this. If we would integrate w prime of t, and you're going to use your calculators in this one because you're not going to integrate this by hand. You're going to use your calculator. That's why they give you as a calculator problem. But right here, if we integrate this from 0, sorry, not 0, from 20 to 25, that will give us, all right, the difference in the temperatures from 25 minutes to 20 minutes. Okay, because you recall, when you integrate, what's the antiderivative of w prime of t? The antiderivative of w prime of t is going to be w of t. And we're going to integrate that using the fundamental theorem from 20 to 25. And so this is going to equal w of 25 minus w of 20. Upper limit minus lower limit. Now, this is the thing, is that when we have this, we don't know what this value is. We're going to use our calculator to help us figure this out. That's going to give us the values of this amount right here. Now, what else do we know? We are trying to find what is W of 25. What is the temperature at 25? We're looking for this. Well, what is W of 20? Well, W of 20, if you look over here, is whoop, that value right there. And so this is what we got. We know that the integral from 20 to 25 of w prime of t, which we're going to find out in our calculator in just a minute, all right, is going to equal w of 25, which we're trying to find, minus w of 20, which we know is 71. And this is where we use the fundamental theorem and an accumulation function, and we're going to add the 71 to their side. So 71 plus the integral from 20 to 25 of w prime of t dt is going to equal what we're looking for right there. Okay, so you need to go to your calculators and you need to enter that in, so make sure you can do that. If you go to math and you go to function, integrate number 9, all right, and you plug in that function, all right, and if you have the TI-84, all right, it kind of lays out everything for you, which is pretty sweet. Okay, it has a cosine. All right, your cosine function is make sure you're in radians when you're doing this, or you can get some really messed up answers. Okay, so I'm going to make sure my mode is in radians. It is. All right. Make sure you put x as your limit of integration, even though it's t, but you can just use x. That's fine. And make sure you're going from 20 to 25 for your answer. And what you get then is this, at least this is what I got, maybe you got the same thing, is that you're going to have 71 plus 2.043, and you add that together, and what you have for your final answer, which is then going to equal W of 25. So the temperature at 25 is going to be 73.043 degrees Fahrenheit. Boom. That is what that temperature is going to increase to. Okay? That's what we have. That sounds reasonable. That seems reasonable. And that's how we get it. So that was part D, fundamental theorem. Really good problem. All right? Not too hard, but you had to understand that going from a derivative to a temperature, you have to write this out. Okay? Please write this out. Write out this as well. All right? Fill it in right here. Add the 71, this right there, and then you can solve, and you get your final answer. Bada bing, bada boom, you got it. All right. So we did Riemann sums, did some fundamental theorem of calculus, and we did some derivatives in the part A and B that we had in my previous video. So I hope this helps you out in solving some additional problems. All right. On free response questions. Remember, this was 2012. Really, really important that you understand how to do ones with tables, especially when you deal with Riemann sums, all right, and the fundamental theorem. You always will see that, something like that. All right, well, Good luck and God bless. Yeah, on the rest of your problems. Bye.